Hello, I'm Michael Koval, a senior staff software engineer at Waymo, formerly known as the Google Self-Driving Car project. Today I'm going to discuss some of the work that our planning, behavior prediction, and research teams have done on interactive planning for autonomous vehicles. Waymo's mission is to build the world's most experienced driver to make it safe and easy for people and things to get where we're going. And I just want to call out in advance that this presentation describes some of the cutting edge research we're doing, not necessarily what's in the production system today. We obviously have a very rigorous release process and take safety very seriously for anything we put on public roads. So I can't comment on whether the specific technologies we're talking about now are running on our fleet or not. But they are definitely something that we're very interested in and actively pursuing. So interactive planning is an important part of driving, and therefore it's an important part of building the Waymo driver. So we really want to be able to drive in situations where humans can drive. And we really have two major product lines. We have a transportation as a service, or sort of a robo-taxi service that is mostly in suburbs and cities. And we have a trucking and goods transportation service, which includes a lot of freeway driving. And interactive planning is important in both of these contexts. In suburbs and cities, there's a lot of lane changes and merges with dense traffic. Think about rush hour in San Francisco, or really anywhere. There's narrow roads where you might have to pull over or wait for someone else to pull over to squeeze through a gap. There's unprotected intersections, intersections where you might have to negotiate with traffic in other lanes to determine who goes first, like turn taking at a stop sign, or deciding which car to take an unprotected turn after. On freeways, there's interactive planning, again, in lane changes and shifts, and you can imagine that lane changing with a 53-foot trailer looks an awful lot different than lane changing in a sedan or a van. There's lane shifts, which are common in construction zones. There's structured merges when you have to get onto or off of the highway, or two lanes merge. And all these are situations where driving really is interactive, meaning that the actions that the autonomous vehicle, the ADV, takes, and the actions that other agents take in the environment, like the vehicles or pedestrians around the ADV, are really tightly coupled. And as an example of that, this is some video footage from one of our Waymos driving through Chinatown in downtown San Francisco. And you'll see that we have a green light here. There's a ton of pedestrians. You'll see that pedestrian on the left stopped for us and let us go. And that's an example of an interaction. And this is actually a quite complicated interaction because you see how many other agents there are. Here's another interaction where a vehicle pulls over to allow us to pass. These are all here's a third interaction where a jaywalking pedestrian in this business district invites another pedestrian to cross, and we wait for them after thinking that we should go before that hand gesture occurs. So you can imagine that driving in these urban environments requires a lot of interaction with other agents. So it's an important thing that our planning team thinks a lot about. And here's another example on a freeway. This is an example of one of our autonomous trucks stuck in fairly heavy traffic and accelerating from a stop due to the heavy traffic. And we need to change lanes to get over due to this structured merge. You'll see there that we were relying on that bus behind us, shown as that pink box, to slow down to let us in. And we do slot into traffic while still leaving enough space in front of us to maintain a safe braking distance. So these are some simple examples of interactive maneuvers. We can imagine they get sort of arbitrarily complicated as you look at more and more tail events. So the key question of this talk is, how can we get an autonomous vehicle to plan safe and assertive maneuvers through interactive situations? And when we think about the way planning is often structured for autonomous vehicles or in the robotics literature, we often think about using search or optimization or a combination of the two. Maybe some of it incorporates machine learning, but this is really planning from the autonomous vehicle's perspective. The way we consider what other agents do in the future is by taking predictions of what their behavior is and avoiding it in search or optimization. So you sort of think of other agents as dynamic obstacles. And this works well in a lot of situations. It works well in situations where the ADV's behavior doesn't have a big impact on how other agents will react in the future. An example of one of these non-interactive situations is this unprotected intersection where the ADV is attempting to make a left and there's a crossing agent that has precedence on a green light. So from the ADV's perspective, I'm drawing the ADV's intent there as an arrow. The ADV wants to cross by making that unprotected turn, but our behavior prediction for the orange agent concludes that the agent will proceed, so it's not safe to cross. Therefore, the ADV decides to yield, correctly, I might add. From the agent's perspective, the agent sees the ADV and sees that it's stopped and concludes that it will yield because the agent has precedence, so the agent might proceed. Therefore, the agent proceeds and doesn't slow down for the ADV to turn. And this is actually working as intended. The ADV appropriately yields to the agent that has precedence. And this is an example where this sort of non-interactive planning, where we treat other agents as dynamic obstacles, works really well. Now, this paradigm does have limitations, and those limitations most frequently appear in interactive situations. Lane changes are one example of an interactive situation. And what I'm drawing here is sort of a simple example where there's only two agents, but this most often comes up in more complicated examples where you have sort of a large number of agents and you need to choose which pair of agents to slot between. And from the ADV's perspective, that agent doesn't know that the ADV is going to lane change. It's not clear from its past behavior. So it's not safe to lane change, so the ADV won't attempt to lane change and it just continues straight in lane. Or maybe it slows down and merges behind the agent if there's room and tries again for the agent behind it. From the agent's perspective, the agent could be cooperative, in which case if the ADV decides to change lanes, the agent will slow down and allow the ADV to slot in. Or it might be sort of inattentive or more assertive or really in a rush to get wherever they're going, in which case it probably won't slow down and allow the ADV to slot in. And in many, many, many cases, if you look at how humans drive, they actually rely on this cooperation. So it would be very hard to merge into dense traffic if you don't rely on any other agents in the scene reacting to the ADV's behavior. Now, of course, you don't want to take the other extreme and force agents to slow down all the time, but there's clearly a balance to strike here that is not as simple as treating the agent's prediction as an obstacle. And in this case, that gap leads to a missed lane change opportunity. So the ADV's behavior is still safe, but it's less assertive than it otherwise could be. So this is the type of problem that we're interested in. Places where failing to model the agent's ability to react to the ADV's future behavior leads to sort of missed opportunities or suboptimal behavior on the part of the ADV. So if we go back to that block diagram where we think about behavior prediction as an input to the planner, that's sort of limiting. And the reason it's limiting is because there's this feedback loop. The planner and behavior prediction, for that matter, run in closed loop. We don't only get one shot to plan the trajectory, so the agent will react to what the planner does. And that creates this feedback loop in interactive situations where what planner decides to do impacts behavior prediction, what behavior prediction predicts impacts what planner decides to do. And if the future ADV trajectory is difficult for an agent to predict given its past behavior, for example, the ADV's been driving straight in lane with no blinker on, then the behavior prediction won't react to the ADV's intent, because the agent doesn't know the ADV's intent. This is an example where, like in the lane change example, the planned ADV trajectory, knowing that the agent should react, is different than the trajectory where it does react. And if we think about how we can break that feedback loop, one option, and the option I'm going to talk about today, is to dispel this idea of keeping predictions as an input to the planner, but really bring them into the planner. And that means to do joint planning for the ADV and interactive agents in the scene. So we're going to be looking at techniques that jointly plan and predict, plan for the ADV, and do behavior prediction for other agents in the scene. So I'm going to talk about two approaches we've explored for doing this. And one approach is more planning-based, the other approach is more learning-based. I'll start by talking about the planning-based approach, which we call ILQ game, short for Iterative Linear Quadratic Games. And this is some joint work by a bunch of teams across Waymo, and I listed some of the key collaborators there, but I just really want to thank everyone involved. I'm just presenting the work here. I did very little of it. And the assumption that ILQ game makes is that we're using an optimizer like ILQR to do trajectory optimization for the ADV. And what I mean by that is that the way we control ADV behavior is we've defined some cost function, CADV, and that cost function in this case is quadratic in the state variables. The state variables are the parameterization for the ADV's trajectory. And we find a trajectory for the ADV to drive by optimizing that cost function using ILQR. And of course, that cost function includes many terms. It really has to represent all the context and nuance in driving. So it represents safety, comfort, progress, various sort of conventions and social norms on the road about how agents interact with each other. And a key part of all of those costs, or at least many of them, is what other agents will do in the future. So many of those costs are parameterized by behavior predictions of other agents. And this is where that input from behavior prediction into the planner exists in the instance of ILQR. Now, if we think about how we implement the behavior prediction model, you can think about predicting the behavior of other agents is also a planning problem. It's just planning from the perspective of other agents instead of planning from the perspective of the ADV. So you can imagine having a separate cost function for each of the other agents and running ILQR on each of those independently, just like you ran ILQR on the ADV cost function to find a trajectory for the ADV. And these cost functions are different than the ADV cost functions, but they're presumably somewhat similar. Many of the same constraints that exist for the ADV, like not colliding with objects, not colliding with other agents, also exist for the other agents. So you'd expect sort of similar behavior, but the key difference is what the ADV is doing is desired and knows the intent of the ADV. What the other agents are doing is a pure prediction based on what the ADV knows about what they did in the past. Now, this again works great when agents are non-interactive. You can think about that this is the flow, that C1 through Cn from the predictions to the planner. And as long as there's no feedback loop back so that CADV does not affect the agent trajectories, then this is a very good model for the problem. However, if we bring in another agent, say an agent that is interactive with the ADV, so say an agent behind the ADV when the ADV breaks, or an agent that the ADV would like to lane change in front of, there exists this coupling. The interactive agent's cost function depends on many cost terms that are a function of where the ADV is, or the ADV's state. And the ADV's cost function depends on where the interactive agent is. And in fact, you would expect it to sort of depend more on that agent and vice versa for the agent depending upon the ADV than the other agents because they're interactive. So clearly it's important for the behavior in the maneuver. And this formulation ignores the coupling of these costs. Basically, we're doing, you can think of it as coordinate ascent or coordinate descent. We're first optimizing the agent trajectory, assuming the ADV trajectory is fixed, then optimizing the ADV trajectory, assuming the agent trajectory is fixed. And of course, that doesn't lead to an optimal solution, or at least it cannot lead to an optimal solution. And the suboptimality looks a lot like the example I showed you before. So our proposal is to formulate this as a linear quadratic game instead of a pure trajectory optimization problem, and solve a joint optimization. And that joint optimization includes variables for both, includes the cost function for the ADV and the cost function for interactive agents. And those are combined using something that weights the relative cost of the ADV and other agents. So you would expect that if the ADV can reduce its cost without impacting the other agent, it would do so, and vice versa. And in the cases where there is a coupling, they sort of jointly negotiate to drive down this joint cost function. And I have to say, I wish I had more time to go into it now, but what operator you choose for that combination obviously has an enormous impact on how cooperative or uncooperative the agent is. So if you sort of heavily weight the ADV's cost function, then the agent becomes very cooperative. If you weight it less so, then the ADV is sort of subject to much more assertive agent behavior. And there's all sorts of interesting middle grounds there. But let me show you some results. So this is a prototype of that system I just described, and it's a little bit hard to see here, but on the left you can see the ADV in green proceeding, shifting into a turn lane with another agent behind it, and you'll see that that other agent doesn't really react to the ADV, and they end up driving through each other. And the right here, you can see the same rendering, but the result obviously looks much better with one agent clearly following the other. So this is an example of how we can get that cooperative behavior by solving a joint optimization. And I'll just play it one more time. So right there you can see that one agent drove through the other, and here you see one red agent following the other. And in more complicated situations, like here's a sort of a narrow corridor that two agents are trying to navigate. The ADV is starting on the right and trying to squeeze between those two vehicles. The agent is on the left and is trying to also squeeze through the same corridor. Now, and the yellow states there are what the future state of the ADV and the agent look like. They're both drawn as yellow contours of the ADV for visualization purposes. So what you see here is a case where the agent is very assertive and gets through the corridor first, and you see it sort of pulls to the right, and then the ADV is able to proceed through afterwards. And the ADV here stopped with enough room to allow the agent to fit through. And then here's an example with the converse, where the agent yields by pulling behind the large vehicle, and the ADV proceeds, after which the agent would proceed through the gap, but that's not shown here. Obviously, these are just illustrative examples. You can see all sorts of artifacts in here around like clipping. That this is mostly visualization artifacts, since we're using the same contour to render both future object states. So I just talked a little bit about how we can use a joint optimization similar to ILQR, but called ILQ game, to combine prediction and planning in optimization. Next, I'm going to talk about a different technique that does the same thing. It combines prediction and planning, but it does it in a very different way. It does it using machine learning. And interestingly, It uses a machine learning technique borrowed from natural language understanding called transformers. So for those of you who aren't familiar with transformers, transformers are a neural net model that consists of two stages, an encoder and a decoder. And the sort of key idea in natural language understanding, so we're talking about words and sentences here, or words and sort of documents, that the encoder and decoder both use a mechanism called attention, which is approximately fully connected layers of embeddings, basically. And that's what's shown in the right there. The sort of initial embedding is in an empty circle, and the sort of embedding after it's been updated using context is shown in gray. And sort of the key insight behind transformers is that you can stack a number of these layers in front of each other. And since they're fully connected, they're very good at extracting context from a larger structure. So during encoding, each word in a layer attends to all other words and their encodings. And then at decoding time, you attend to, again, all previous encodings, but also all previous words you predicted. And this provides the context, for example, to create a coherent sentence where, say, pronouns refer to the correct objects earlier in the sentence. Now, and these have shown enormous success. BERT is an example of this. These networks are state-of-the-art, or derivatives of these networks are state-of-the-art in natural language understanding. They also perform very well on TPUs, which is one of the reasons they're able to consume an enormous amount of data to reach that level of performance. So so you might wonder, like, this is great, but we're talking about self-driving cars, not translation from English to French. And that's true, but if you look and you really squint, sentences look an awful lot like trajectories. They're a sequence of waypoints. And words look an awful lot like waypoints. They're sort of a discrete unit in a trajectory that have some context that is represented by features that are embedded, that can be summarized in an embedding. So you can think about the equivalent of attention on words to be attention on trajectory waypoints or on context associated with those trajectory waypoints. So the key insight behind scene transformer is to represent the prediction and planning problem as a machine learning problem, a sequential prediction problem, and then to solve it using a transformer-based machine learned model. So this is a quick summary of the architecture. There's basically two inputs. There's agent features from perception. There's road graph features from perception and maps. This goes through a number of attention layers, some of which are self-attention within the agents, and others are cross-attention between the agents and the road graph features. And then the decoder has additional attention layers plus maximum likelihood decoding to produce basically a probability distribution. So this is the high-level idea of the network architecture. And if you think about laying out the other the ADV and the other agent states in a grid, you can think about attention sort of along a row, so that's attention along an agent state, as enforcing temporal consistency over the trajectory. So it basically learns smooth trajectories. And attention across agent states, so that's along the same step in time or nearby steps of time, as learning the way multiple agents interact. So if the ADV is interacting with another agent, you would expect there to be high weights on that column in this matrix, high weights on the amount of attention that the ADV embedding gives to those other agents' embeddings. And ditto for road graph context. That's just a separate matrix that I think is less interesting from an interactive perspective. And the interesting thing about this is the way you train a transformer is by masking different parts of the input data. So on the ground truth data, we know what all of those cells are, and you can mask some of the cells and ask the transformer to predict the missing ones. And the ones that are missing at the ones that are missing at inference time when you ask to predict are basically the output of the model. So you can imagine that if you only mask, so we always know the history, we always know what happened before time t. After time t, if you know nothing, then it's a pure behavior prediction problem. If you know what the ADV is going to do, but you don't know what any other agents are going to do, so you only unmask what the ADV does, then it's a conditional behavior prediction problem. And if you know if the only thing you don't know is what the ADV is going to do in the future, if the only thing that is unmasked is what the ADV is going to do in the future, then you can basically specify a goal. And you can think of that as somewhat similar to the planning problem. So you're basically telling the ADV where you want it, you're telling the transformer where you want the ADV to be at a certain time step, and you're asking the model to predict how it got there and how all the other agents reacted to the ADV getting there. And the really exciting thing about this, well, I think it's exciting that we have sort of one architecture that can solve the planning, behavior prediction, and conditional behavior prediction tasks. But an even more exciting thing is that we can train one model to do all three things, or any subset of the things that we desire. And we can actually use that model to perform inference on any of these at inference time. So you can imagine just round robining between the different mass structures during training time, and the ratio at which you round robin them is basically the amount you're training the model to perform each of these tasks. Then at inference time, whatever you mask out is what gets predicted, and that's the task you're asking the model to perform. And this works really, really well. So just running this on this sort of marginal behavior prediction problem. So we're querying one agent per segment, and we're running the model in BP mode. So we're basically we're running it in the mode where we only unmask one agent. We achieved the best published min ADE and min FDE on the Argoverse data set compared to published results at the time. I believe it's still competitive with the leaderboard today. So this sort of suggests that, well, while we design this method to work for solving this joint prediction, planning, and conditional prediction problem, it is actually quite effective as only a behavior prediction problem. And that's not terribly surprising, I think, because like interaction is clearly important for predicting good agent marginals. So the fact that making a model that's designed to predict good interactions produces good agent models, agent marginals is sort of a nice confirmation of our intuition. However, the place where this gets more exciting is when we look at the results on the Waymo open motion dataset, which explicitly includes interactive prediction problems. So this is a subset of the data where there is a lot of interaction between agents in the scene. And for this, we actually tried running all of the masking strategies. So we tried marginal, which is only unmask one agent state. There's BP only, which is produce all future agent states. There's planning, which is to, again, only unmask the final ego state and give the task a goal, and give the network a goal. And then there's a multitask, which is to cycle through the above uniformly at random. So basically train the network to perform a equal mix of all three tasks. And then we looked at two experiments. One is to the marginal prediction experiment, where we return sort of one prediction for each agent that best summarizes the future state. The other thing we did was joint prediction or interaction prediction experiment, or return all futures. These are really joint futures. So like we not only know that agent 1 can do X and agent 2 can do Y, but we can make the statement that if agent 1 does X, then agent 2 will do Y. And I'll show you an example of that in a second. And the interesting takeaway here is that, well, Marginal performs best on motion prediction. That makes sense. That's the way we're evaluating it. So the fact that the network trained to only do that one task performs well is not too surprising. You'll note that the other models perform okay. They're worse than the baseline, but they're not orders of magnitude worse on really any of the metrics. The interaction prediction is where this is really interesting. This is where the joint BP only model outperforms Marginal on interaction prediction, and this is a pretty significant improvement. And then it also, I think the really exciting thing is adding the planning version of the model doesn't regress the results, and in fact it almost unilaterally improves them. So the multitask model, which has this additional task to perform a planning problem, actually performs better at behavior prediction for interactive prediction than the other model. And this is really exciting because these are really high capacity models. So they scale very well with more data, which suggests that this model has an architecture and enough capacity that it could scale to jointly perform all tasks, all three of these tasks, without really sacrificing performance on one to improve the other. Or at least that's what we hope based on these results. So to show some results, this is a video of one of the Marginal prediction tasks. So this is just rolling forward in time, and this is just the most likely prediction. And this is a video of the same starting scene or a similar starting scene with a joint prediction task. So the way this is rendered is sort of like a particle filter, or we're rendering a bunch of samples from each agent future, but these are actually joint samples. So we know how these samples are associated with each other. So you can think of it as there are 10 or so joint futures. There's not 10 samples per agent state that are combined, and per agent that are combined in an unknown way. I think this is really exciting because the ADV is one of these, and this means that we're able to model joint prediction in a way that, for example, would predict that if the ADV were to lane change, the other agent would slow down, and we know how the other agent would slow down, and that is really, really useful from a planning perspective. So one shout out is that these results are from the Waymo Open dataset, specifically the Waymo Open Motion dataset. And if you're interested at all in interactive planning or in prediction, I strongly encourage you to check this out. Our research team and many of their collaborators put an enormous amount of effort into cleaning up and publishing this data, and I think it's a great resource that you should really consider using. So to wrap up, what I talked about today was how and why separating prediction from planning has limitations in some interactive situations. And those limitations really are that there's this missing feedback loop that isn't modeled in that architecture between what impact the ADV's future trajectory has on its behavior predictions. And the solution I proposed, and I discussed two techniques for doing so, are to combine prediction and planning into a joint model. And the two techniques we talked about were ILQ game via ILQR trajectory optimization, and scene transformer using attention models in a neural network. Now, I think these results are really exciting, and I'm really happy with the way these projects worked out, but there's certainly more work to do. And 4 challenges I specifically want to call out. One is evaluation. It is very difficult to evaluate interactions because it's very much a counterfactual question, where as soon as the ADV changes its behavior, there's no longer any ground truth data about what other agents will do. And it's not possible to get back in that scene to recreate what would have happened. So it's a huge challenge to tell, are these counterfactuals that we're producing realistic? And what does realistic even mean? Are they realistic in the ways that we care about for the things we're trying to measure? Second is safety, and this ties into the evaluation problem. Our models aren't going to be perfect. So it's possible that we'll predict an agent is more cooperative than they actually are, or vice versa. And in the case where we predict that they're more cooperative than they actually are, we need a way to guarantee that we can still react in a way that is safe. Perhaps maybe by braking harder than we otherwise would have and sacrificing a little bit of comfort to maintain safety. So this requires sort of a lot of thought about how do we incorporate uncertainty into these, what agents do in the future, into really the core of the planning algorithm, such that when agents react in an unexpected way, we're still able to guarantee that we can handle it. Third is scalability. Planning joint futures, the number of joint futures there are blows up exponentially with the number of interactive agents. So we need to think really hard about clever techniques for reducing the number of agents that we care about interaction on, or ways of handling large number of agents in a more efficient way who are interactive. And this is, I think, both an interesting algorithmic question, and how do we structure the algorithm to take advantage of the structure of non-interactive agents, or sort of simplified reactions to do that efficiently. And also a really interesting computer sort of infrastructure question, where how can we change our software architecture or the planning architecture to do more of that work in a timing budget so we can still have a acceptable reaction time. Finally, I presented two approaches today, and there's surely more. I'm sure everyone in the audience has all ideas for interesting approaches to pursue for solving the interactive planning problem. Now, how do we combine them? Because clearly the ML approach I talked about has benefits, like the ability to consume huge amounts of data via the high capacity nature of the model, but so does the optimization approach, like the ability to enforce hard constraints. And it's super, super interesting to think about what combining those two approaches would look like. It's also interesting to think about what a similar approach would look like in a more traditional search algorithm, or a different optimization algorithm, or perhaps a different machine learning model structure. So these are a few areas that I think are sort of exciting opportunities for future work. If you're interested, I will say that we're hiring, and this is a topic that is very, very dear to us. So please go to our website and apply if you're interested. So thank you. If you have any questions, please attend the live Q&A session or reach out by email. And if you're interested in joining us to work on these problems or many of the other interesting motion planning, ML, or simulation and eval challenges that we have, please go to our career website. And I listed a few